We want to find the area under the graph of y equals x squared above the x-axis. Now, we know we can approximate this area using rectangles. If I add some rectangles here, however many, 4, 5, 10, 100, however many rectangles I might do. Here I'll just draw a picture with, say, 5 rectangles, but just let them represent whatever number of rectangles you want. Whatever number of rectangles. Here are rectangles. You can use rectangles to approximate the area, where we'll make these rectangles all have the same width. We'll say that we have n. These are right endpoint rectangles, right endpoint rectangles. And if there are indeed n of them, then the width of each one would be 1 over n, because my total width here is 0 to 1. You divide that by n. I have n right endpoint rectangles. Now what I want to do now is I want to ask, in general, what do the area of these rectangles come out to be? What is the area of n right endpoint rectangles? Not just when it's 4 or 8 or 16, but can I get a formula for any n? And then if I want to, I could plug in 100 or 1,000 or 1,000,000 to get my approximation. Okay, here we go. So I have n of these rectangles, and I want to figure out what's the area of them. So the width of each of these rectangles is going to be 1 over n. So my width is 1 over n for this first rectangle. And the height for the first rectangle, well, this is at the x value right here of 1 over n. So the height will be 1 over n squared, because I need to plug that into my function, y equals x squared, to figure out the height of it. Plus, for my next rectangle, the width is again 1 over n, but now this is at 2 over n. That's the x value it's at. So it's 1 over n is its width, times the x value, 2 over n squared, to give you the height. And you keep going this way. It'll be 1 over n times 3, so here I'm at 3 over n, and I just keep going until I get finally to 1 over n times the last guy, which is 1, but you can think we got to 1 because we got to n over n. We went n times n steps to get to n copies of 1 over n, and then we're going to square that. That's just 1. And okay, what does this come out to be? Well, we can simplify this a little bit. One way to do that is I could write this as pull out that 1 over n, and then here I just have 1 squared over n squared plus 2 squared over n squared all the way through n squared over n squared. Yes, that's just 1, but there's a reason I'm writing it like this. Okay, I pulled out this 1 over n, I pulled out these 1 over n's, I pulled them out, leaving me with this expression. 1 squared over n squared plus 2 squared over n squared through n squared over n squared. Actually, I could also pull out this n squared on bottom. So I could make this a 1 over n cubed, pulling out the n squared, times them by n to get 1 over n cubed, and be left with just 1 squared plus 2 squared all the way through n squared. Now, at this point, remember back to our formula for a sum of 1 squared through n squared. So we had a separate video about this, about the summation formula. This is just a summation formula. This would just be 1 over n cubed. This is just the sum of I squared, where I goes from 1 to n. Our summation formula says that this sum just comes out to be, do you remember it? So the sum of n came out to be n times n plus 1 over 2. The sum of n squared came out to be n times n plus 1 times 2n plus 1 all over 6. So there I have it. Here is my formula for the area of n rectangles. If you plug in n equals 4, you get estimates like we saw before. Or n equals 100, you get better estimates. But what if I want to know the true area? What is the actual area under the graph, above the x-axis, between 0 and 1? What does that actual area come out to be? Well, I could plug in really big numbers of n to get good estimates, but instead of just plugging in one particular big number, like 1,000 or 1,000,000, what I'm going to do is I'm going to take the limit. The limit as n gets bigger and bigger and bigger going to infinity. If these rectangles get smaller and smaller and smaller, n as 1,000, n as 1,000,000, n as 1,000,000,000, then it'll come to, in the limit, giving you better and better and better approximations until it gives you the exact area. So the area is the limit as n goes to infinity of this formula, of n times n plus 1 times 2n plus 1 all over 6 times n cubed, my 6 times my n cubed. So I can find the area just by calculating this limit. Now, do you remember how to find the limit of polynomials? When you have polynomials, what we can do is, well, we can expand this polynomial on top. So n plus 1 times 2n plus 1, that's just going to be, let's calculate this out really fast. This is 2n squared plus 2n plus n, so plus 3n plus 1. Then you need to times it by n again. So up top we have 2n cubed plus 3n squared plus n all over 6n cubed. What happens as n goes to infinity? Well, as n goes to infinity, you can disregard these smaller terms, and it just becomes this ratio. It's just 2 over 6, or 1/3. 1/3. And indeed, in the previous video, when we estimated this area, we got estimates that told us it was right in the ballpark of 1/3. So now we've been able to show that the area under the graph of x squared from 0 to 1 is exactly 1/3. If you take the limit as n goes to infinity of more and more rectangles, it approaches precisely 1/3.